We have ASM Risby. He is a PhD candidate at the University of Southern California. His research interests include networking, security, and the internet measurements. He works in the analysis of network traffic lab, which Professor John Heidenman leads. He will be talking about Anycast polarization in the wild. So, Risby, whenever you're ready.
Yes, let me share my slides. Can you all hear me?
Yes.
Okay. Can you see my screen? Okay. All right. Thanks, Elisa, for the nice introduction. I'm Rijvi. I'm a PhD candidate at USC and I'm also a senior site reliability engineer at Akamai Technologies. I'm going to talk about our work titled Anycast Polarization in the Wild. This is a joint work between USC ISI and Akamai Technologies. This work was presented in the recent Passive and Active Measurement Conference. Okay, so let's get started. So in Anycast, we see multiple sites that distributes the whole world into multiple catchments. As you can see from the figure that there are three particular catchments or particular Anycast sites that are located in 3 continents. We call a problem of polarization when some clients from a continent go to the nearby location and some other clients from the same continent are not going to the nearby location. They're going to a distant site. For example, here you can see 2 European clients. One is going to the North European site and the other one is going to the North American site. We call this type of scenario as polarization. On the other hand, you can see there is a client in South America who is going to the North American site. But we are not calling this type of scenario as polarization since this South American client doesn't have any nearby site in South America. The term polarization actually was used by Giovanni Mora in his 2020 IMC paper, but we use polarization to explore the real world scenarios where we have polarization problems. The impact of polarization is added latency. As you can see, the European traffic is going to North America, so it adds latency. And we observe over 100 milliseconds of added latency due to this kind of polarization. So in this work, we make 3 contributions. Our first contribution is we try to find out the potential reasons behind polarization, and we propose an algorithm to find out the polarization problems and their key reasons. Our second contribution is to evaluate around 8,000 Anycast prefixes to see what's the real world scenario is and how many of them have this kind of polarization problem. Our third contribution is to show how we can improve the situation with the polarization problem. We worked with a CDN and we use different traffic engineering techniques to improve the situation. So what's the ideal Anycast world? What do we expect from an Anycast world? So as I already say that Anycast divides the whole world into multiple catchments. So in an ideal world, we want the clients should go to the nearby location. As you can see here, there are 3 sites and all of these 3 clients are going to their nearby site. And that's our expectation from an Anycast network. But this is not the case in reality. In reality, you will see some traffic will go to a distant site, even though they have a nearby location. So next, we will find out the reasons behind the polarization problems. So we find 2 key reasons behind polarization. The first one is multiple backbone problem, and the second one is regional leakage problem. And We find these two key reasons in the wild Anycast networks. Next, we will discuss about these key reasons. Okay, so the first reason behind the polarization problem is multi-pop backbone problem. So here you can see there are two sides. One in there are two pop. Pop means point of presence, which we use for representing Anycast site. So there are two sites, one in North America and one in Europe, as you can see from the left and the right side. In the ideal world, the North American client should go to the North American site and the European client should go to the European site. The difference between these two sites is the North American site is directly connected to a tier 1 backbone, which is by tier 1 we mean the big giant ISPs like NTT Tata, who have a very good global coverage. The difference is the European site doesn't have this direct connectivity with the tier 1 backbone. As a result, we observe, and this tier 1 backbone has a global coverage. So this ISP-B, which is possibly a European ISP, which has mostly European clients, is a client of that tier 1 provider. So as a result, what will happen, this European client will take this path to the North American site, even though it has a nearby location in Europe, because this ISP-B is a customer of tier 1 backbone, and they have to rely on this tier 1 backbone to get their service. This problem happens because the European site doesn't have any direct connectivity with the tier 1 backbone. In our second class of problem, we have regional leakage problem. This is kind of similar with the previous problem that we showed, but in this case, the tier 1 provider is not directly connected with the North American site. So there is a regional AS which is propagating the routes to the tier 1 AS, and through that tier 1 AS, some clients will go to the North American site from Europe, even though they have a site in Europe. So this kind of problem happens because this tier 1 AS is not connected in any way to the European side. And the difference between the previous one and this one is the tier 1 AS, it's not directly connected here, but in the previous one we had the direct connection with the North American site. All right, so we find the two key reasons behind polarization. Next, we will show how we find this kind of polarization problems and their reasons. So finding the polarization problem follows from how we define the polarization problem. So when some clients from a continent get good latency or go to the nearby location, and some other clients go to a distant site, we call that type of scenario as polarization. But how can we know the distance, like how they're where they're going? So we use a latency threshold to indicate whether they're going to the nearby site or a distant site. So we use 50 milliseconds of latency. If some of the clients from a continent are getting less than 50 milliseconds of latency, we call it going to the nearby location. And if some other clients from the same continent are getting over 100 millisecond latency, we call it they are going to a distant location. So from a particular continent, if we find both of them, then we call this type of scenario as polarization. And we use this approach for all the known Anycast prefixes. We collect the list of Anycast prefixes from an earlier work from IMC, and we got around 8,000 Anycast prefixes, and we ping to all of them from RIPE Atlas vantage points. So after getting the initial list of potential polarization problems, we make trace routes from the right vantage points to those Anycast prefixes. I'm not going over the details of this algorithm, but we try to find out the penultimate hop, and if the penultimate S hop is a tier 1 provider, then it's a possible multiple backbone problem, since it's because of this tier 1 provider. If it's not, then it's possibly a regional routing problem, if it's not a tier 1 S. There are some other sub-classifications, but I'm not going over the details. You can find them in our paper. So next, we show how common is polarization. So in real world, how much Anycast networks have this kind of problem. So as you can see from the table that around 28% of the known Anycast prefixes had potential polarization problem when we made the measurement back in 2023. So we found around 2,273 Anycast prefixes which might have polarization problem. We confirmed 18 one of them with the operators, and they verify our findings, and they really had this kind of polarization problems. A common belief is when we have more number of sites, we shouldn't have this kind of polarization problem. So to answer this question, we try to find out whether that's really the case. So as you can see from the x-axis, we show the number of sites, and from the y-axis, we show the percentage of Anycast services that observe the polarization problem. So you can see that when the number of Anycast sites is 30 or below 30, we have more polarization problem, but it's not uncommon, completely uncommon, that we may have a polarization problem when we have over 35 sites or maybe 35 sites. So in summary, we can tell that it's more common with less number of sites, but it's not also uncommon when we have more number of sites like 30 or 35 or 40. Okay, so next, the impacts. As you can see from the red box, that the impact of polarization problem is making the difference between the median and 95th percentile latency bigger. As you can see, in many cases, we have 12 milliseconds of median latency, and the 95th percentile latency becomes 173 milliseconds, so which is a huge difference. And that basically because some of the clients are going to the really nearby location, which is like 12 milliseconds away, and some other clients are going to a distant site in other continent, which is 173 milliseconds away. As some examples, you can see in the rightmost column that some traffic from Poland is going to USA, some traffic from the USA is going to Singapore. So they're traveling the whole world, even though they have a nearby location. And in the first column, you can see there are multiple CDN operators or DNS operators that have this kind of issue. And I'm not, we are anonymizing the names here, but we find it for many CDNs and DNS and cloud providers. Okay, so we work with some operators to improve the situation. Next, we will show them. As you can see, there are some ways for improving the situation. As we said, we should have good connectivity with the transit providers. We should have more number of Anycast sites, and we should be vigilant about route leakage. And the way we improve the situation with the CDN operators is using some kind of routing changes to improve the situation. Next, we will show those kind of situation. So in this slide, you can see a real world scenario that shows the polarization problem. Here we are showing three maps here, three global maps. Each map indicates a particular Anycast site. For example, the first one indicates it's the Dallas, the USA catchment. The second one is the Virginia, USA catchment. And the third one is the Milan, USA catchment. And the red dots or the green dots, I mean, any dot is indicating that these clients from all over the world are going to the Dallas location. in the first graph. So some European clients are going to the Dallas location, some Asian clients are going to the Dallas location, and the colors are representing the RTT. As you can see, the red means it's over 100 milliseconds of latency, and the green means less than 50 milliseconds of latency. And since this site, the first one is for Dallas site, the US probes clients are getting good latency, which is less than 50 milliseconds. So what's the reason behind this polarization problem? It's the same kind of slide that we showed for telling the reason. Here, instead of a tier 1 AS, it's the AS1299, which is a big tier 1 provider that is connected only in Dallas, but not in Europe. As a result, the clients from Europe are going to that location. So how did we improve the situation? We just blocked those announcements to those tier 1 providers who didn't have well connectivity or direct connectivity with all the sites. As a result, you can see in the right side, the situation got improved, and there are less number of red dots, and you can see in every continent we observed improvement. And by the way, these are all real world improvement after making just a single change. So in conclusion, polarization is not uncommon. We find polarization in 23% of the Anycast networks, Anycast prefixes. We find two key reasons behind polarization problem, and we show that routing changes can improve the situation. Thank you all. I'm ready to take any question.
Thank you very much. Thank you very much, Rizvi. We have any questions for the room? We are a bit late. So does anybody have any question? Otherwise, I have one. So Rizvi, okay, we have a question from the room. Please state your name and company and go with the question. Thank you.
Hola. Okay, my name is Thomas Lynch, Vulture AS20473. Can you go back to slide 15, please?
Sure.
Because I was doing a kind of this presentation, not so much in detail, but I would like to highlight that you have regional transit providers like Singtel and Hurricane Electric and Sparkle that do not have presence globally, like, for example, NTT, Massimo's NTT. And I have found that using regional transit providers create more polarization, as you're calling it, than global transit providers.
Yeah, I think you're right that these providers are not that much big like NTT. But we found the case that these providers actually propagates the routes to their upstream providers, and their upstream providers are really big tier 1 providers, and that's why they're sinking a lot of traffic, and that's why they are creating the polarization problem. So it's not about like you have to have big tier 1 providers which do not have global, which are not directly connected in multiple locations. But in some cases, you just use some regional AS, and those ASs are propagating the routes to the tier 1 providers, and that can create the polarization problem as well. And at the same time, in some cases, this some of the Anycast network providers, they just use these small ASs as their transit providers, which is really surprising. And that's why sometimes we get this kind of polarization problem as well. Does that answer your question?
Thank you.
Somewhat?
Thank you very much.
Thank you very much. Thank you very much, Rizvi. Big applause. And